Greetings everybody, so in the previous video we introduced topological spaces, and in today's video we're going to be taking a look at a very important example, which is the so-called standard topology on Rn, which is a set we use all the time, so it's quite important. So before we take a look at Rn, let's just take a look at R. So R, what do I mean by R? I mean, well, the real numbers, and we usually think about R as this nice straight line over here. We have 0, 1, and yeah, all the numbers, all the real numbers on this nice line. Now, in fact, it's actually a little bit illegal to draw R out like this, because drawing it out like this, we already assume a topology on this. There's actually already a topology on this line if we decide to draw it out like this. At the moment, we're only taking a look at R as just a bare set. So again, what is a set? Just to emphasize it, it's just a big bag full of elements. And what are the elements in the set? These are just the numbers on the real line that we're used to. So for example, 0 is in there, 1 is in there, square root of 2 is in there, minus 1 is in there, pi is in there, 3 is in there, even though there's still some controversy if those are distinct elements or not. But yeah, this is what R is. There's, of course, many more points. This is how you should think of R, just a big bag full of all these points. And what the standard topology is going to do for us on the set R is it's going to kind of rearrange all these points a little bit, and it's going to form the real number line, how we're used to seeing the real numbers. And we can generalize this to R2 as well, so the plane. Again, this is illegal because drawing the picture out like this already assumes a topology, even a metric as well, and yeah, so on. We can generalize to Rn. But before we do that, we're just going to take a look at R. So the standard topology, as I said before, it gives us the real number line that we know. Now, to maybe motivate where the standard topology comes from, it's worthwhile taking a look at some other topologies on the real number line. So I already introduced some examples in the previous video. One of them, for example, is the so-called chaotic topology. So what we can do is we can equip R with the chaotic topology. And remember, what is the chaotic topology over here? It is the set consisting of the set we're working with, which is R, and the empty sets. Now again, it is a bit illegal, but for the sake of illustration, I'm going to draw out the real numbers as a nice number line like so. So if you want to see what the chaotic topology is, well, we know the real line is in there, and we know the empty set is in there. So these two subsets of R, this forms the chaotic topology. Now remember, why is the chaotic topology called the chaotic topology? It's because, well, the only neighborhoods we're considering is the empty set and the real number line. And yeah, since the only non-empty neighborhood is the real line itself, basically everything, all the real numbers, is one big neighborhood. So everything's kind of chaotic in that sense, because this whole big bag is one big neighborhood. So this chaotic topology, that's what we refer to as a coarse topology. So there's not many neighborhoods in there. In fact, this is the coarsest topology you can put on a set, the chaotic topology. And how about on the other extreme end? This is the finest topology you can put on a set, and this is the discrete topology. Now, what is the discrete topology? Well, it's simply the power set of R. Now, R is already uncountably infinite, so if you consider the set of all subsets of R, well, that's a ginormous set. Now, the way I like to think about the discrete topology is that you have your real number line over here, and what you actually do is each point on your real number line, it actually is kind of inside of its own little neighborhood, because after all, the discrete topology is the set of all subsets. Each of these points over here, they're definitely subsets, so they can have their own little neighborhood around. And of course, these are not the only neighborhoods you could have. You could have neighborhoods of multiple points and so on. But if you zoom all the way in, what you'll see is that each point is in its own little cozy neighborhood. So that's what the discrete topology is. So as I said before, there's many more subsets, but the discrete topology, that's just the power set of R. Now, maybe just one more example. We could take another topology over here. Maybe you just call it tau prime. What could tau prime be? Well, I'm going to construct another topology. Let's say this is the real number line over here, or the real numbers. And so this is definitely going to be a subset from the axioms. Again, the empty set must also be in there. And let's throw in some more subsets. Let's throw in the interval. Let's say this is 0. Let's throw in the interval from -1 to infinity. Let's throw in the interval from 1 down to -infinity. And since intersections of neighborhoods need to be in there as well, let's throw in the interval from -1 to 1. Now this over here kind of splits your real numbers into some partitions, I guess. So if you imagine your real numbers as a big bag over here, then you have these neighborhoods. It kind of makes this little Venn diagram. So it kind of splits it up into these chunks over here. So this tau prime, you can check it's a topology, satisfies all the axioms. This is still quite a coarse topology. R is an infinite set and there's only, what, just 5 neighborhoods in here. So this is still quite coarse. So these are just some examples of topologies on the real number line. And what we want to do now is we want to construct the standard topology, and that topology gives us the way we understand R. Now the chaotic topology, that's not very useful because we know on the real number line, not everything is bunched together in one big bag like so. And the discrete topology on the other extreme, that's not too useful as well, because what you're doing with the discrete topology is each point is in its own little neighborhood, and that's actually going to have problems when we take a look at continuity. Because in fact, if you equip the real numbers with the discrete topology, then every function on the real numbers is in fact continuous, which we know that's definitely not the case. And a nice way you can think about it, for now, we'll introduce continuous maps later, is because since each of these points is in one of its own little neighborhoods, it doesn't really care about what the other points around it are doing or how it's moving around. So if you map it, however you map it, they're still in their own little cozy neighborhoods. They don't really care about what the other points around them are doing, and then you can kind of tear them apart and whatnot, and yeah, that function or whatever would still be continuous. So discrete topology is not really useful because this definitely does not model how our real numbers, or at least how we think about the real numbers. So what we're after is not something that's on these extremes over here of the most coarse topology or the most fine topology. We're after somewhere in the middle. And the best way to kind of see where the standard topology comes from is by taking a look at what we don't like about the discrete topology. And that's exactly what I said before. Each point is in its own little cozy neighborhood. That's definitely not what we want, because we know on the real number line as we draw it, if we take a look at one point, we definitely know that there's a little neighborhood around there. This point does like to interact with other points near it. So what's a good way to construct a neighborhood that kind of includes points around every single point? Well, that's with some intervals. So over here, let's try to construct what the standard topology would look like. So I'll usually call it tau standard like so. And how can we construct this over here? Well, of course we need the real line. That's always in the topology. Now, we know around each point there's going to be a little neighborhood. And how do we make a neighborhood? Well, we can define some kind of interval. Now, it's not too clear if we want a closed interval or an open interval. I'm actually going to not refer to the word closed and open because those have their own definitions in topology. We covered that last time. So what I'll actually refer to is intervals without boundaries and intervals with boundaries. So at the moment, it's not too clear if we want intervals with boundaries or without boundaries, because around a point, we can still define a neighborhood around that. Now, it turns out that working with intervals without boundaries is a lot nicer, because if you have intervals with boundaries, then if you take a look at the axioms from topology, you know that the intersection of two such intervals, of two such neighborhoods, must yet again be a neighborhood. And if you consider this example, for instance, then what happens if you intersect these together? Well, we just get 1 point, and you're saying, well, that's a neighborhood, but we definitely don't want a singular point to be a neighborhood. We don't want to single out a point. We always want this point to be included in some other neighborhood. So this is actually why we don't want intervals including their boundaries, because it's going to produce points that are singled out in their own little neighborhood. And that's exactly why we don't really like the discrete topology. And if you're still not convinced about why we like to have little neighborhoods around points, take a look at continuity, because when we map the real numbers to something else, we always want points that are close to each other to remain close to each other. For example, of course, we'll make these definitions clear later, but if you take a look at a function, for instance, and if you take a look at small neighborhoods around the points, well, of course, they kind of stay close together. Whereas if you introduce some kind of discontinuity now, then as you can see, small neighborhoods around this point, well, they don't really stay close to each other. There's a little gap here now. So that's why we don't want to single out points over here. We always want to include them in the little neighborhood, because that's how we understand continuity in the real numbers. So yeah, in the standard topology, it's going to consist of all these nice little open intervals, and I don't really care about how big I make them. I could make them really big, or I could make them really small. Those will constitute all our little neighborhoods. So all these intervals that don't include the boundary, those are actually going to constitute our standard topology. And yeah, from the axioms, of course, it's allowed that you could have intervals that are disjoint. So for example, you could have this interval over here where it's disjoint because you can generate this from taking the union of two disjoint intervals. But yeah, all these such intervals that don't include the boundary, those are going to become part of the standard topology. So in the standard topology, what we're actually after is the set of all intervals that don't contain the boundary. That's exactly what the standard topology is. And what this allows us to do is capture the neighborhoods around the points. So this is how we're defining the standard topology on just R. How can we generalize this to Rn? Well, I guess it's easiest to draw this for R2 over here. So yeah, of course this picture is a little bit illegal at the moment, but yeah, we have to draw it out somehow for illustration. So in R2, what does a particular neighborhood look like? Well, it just looks like some set over here that doesn't include its boundary. And because these sets don't include their boundary, and this is what constitutes a topology, we actually call these open sets. All these over here, they're called open sets. And that's actually how we usually think of open sets in the real numbers. So the reason why we call intervals open in R is because they're part of the topology that we define on them. Yeah, all these little subsets over here in R2, that don't contain the boundary or are open are part of the topology. And as soon as you have a little part that's closed or a part that includes the boundary, this is no longer in the topology. It's no longer a neighborhood because yeah, we like things to not include their boundary as discussed before. And yeah, in R3 it would look like a bit of a blob over here, kind of some volume kind of shape. And yeah, you can't really visualize that in R4 and done. So this is basically what the standard topology is. So the question is now, how do we actually construct the standard topology? This is just our rough idea of what it is. How do we construct it rigorously? Well, we need to make one little observation, which is, let's just take R2 again because it's nice and easy to draw. If this is an open set or a set that doesn't contain its boundary, notice that we have one nice observation. It's that if you take a look at every point in this set, you can always find a small little neighborhood around it. So no matter how close you get to that boundary there, you can always construct a small little neighborhood around there. And of course, if you're dead in the middle, then of course there's a little neighborhood, but yeah, you can get as close to that boundary as you want. And there's always a little bit of wiggle room because it's a nice and open set. So this is actually a really nice way to test if a set is open. And you can see if a set has a little bit of a boundary here, then the points on this boundary are actually included. So if you pick a point on the boundary, you're actually not going to be able to find a little neighborhood that's contained in this set. There's going to be this little overhang in here that we don't want. So this is actually a nice test for finding these open sets. Before we do that, let's go back to Rn and let's spell this out explicitly as a set. So Rn, what is Rn? Rn is just the real numbers, but Cartesian product together n times. So this is what Rn is, so Cartesian product n times. And as a set over here, this is the set of all these tuples of numbers x1, comma, dot, 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 xn, such that each of these components over here, these are real numbers. So this is what Rn is. So Rn, don't even think about it as some Euclidean space or something. Just think about it as a big bag for now, where each point takes this form. Okay, so back to the picture where we had those nice open subsets. What we're going to do now is define these so-called open balls. And this open ball is actually what we're going to use to test if this set is indeed open. So this set over here, this little open ball, that's what we're going to define as B sub R of X. So if you pick a point X in here, then how do we define a BRX? Well, first of all, it's definitely a set. Now, it's the set of what? It's the set of all the points in here that lie within a distance R of X. So how do we construct such a thing? So we can take the set of all y1 dot 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 yn, which lie in Rn, such that the distance between whatever point this is and the point X is less than R. Now, distance is not something we've defined. We haven't even defined a metric on Rn. At the moment, it's the set. It's just a bunch of points in this big bag over here. So instead of defining a distance and so on, we're just going to say such that, I'm going to write down the expression first. So that's this square root of the sum running from I equals 1 to n of yi minus xi squared is less than r. Now, you may recognize this. This is how we usually define distances in Euclidean space. It's just Pythagoras' theorem, essentially, and we're requiring that the distance be less than r. So this is how we construct the set of Brx, so the set of all the points that lie within a distance r of x. Now this guy over here, we're actually going to take for granted that we know how to do addition, subtraction, and yeah, just basic arithmetic on r. We're going to take that for granted and use it to define this condition. And yeah, if you had a metric on r, you could replace this with some distance function or something, but we're just going to spell it out explicitly like so. So yeah, Brx, that's just that little ball of radius r. Okay, so back to the open sets now, our topology. We know that every single open set in our topology has the property that for every single point in that set we can construct some kind of small neighborhood, which means that we can construct some kinds of small ball around this, exactly this Brx. So the way we're going to define the standard topology, so our standard over here, we're going to define it as being the set of all subsets U in Rn. Now I don't want any subset. If I just closed it off over here, this would be the power sets. We don't want the power set because that gives a discrete topology. We want to have a bit of a restriction on it. So what's the restriction that we're going to have? Well, I kind of said it before. We require that for all points x in the subset U, we can find a small little neighborhood that's still contained in U. Or equivalently, there exists some positive real number r such that Brx is contained inside U. So this funny kind of expression over here, that just simply states that we collect up all the subsets in Rn such that we can find a small little open ball around every single point that still lies in that set. If we had a little boundary over here, then of course this subset wouldn't be included in this standard topology. That's exactly what we don't want to have, because this condition over here doesn't hold, because we could take this point x over here, and no matter how small you make that ball, no matter how small you make that radius, well, there's still going to be that overhang, so it's not entirely contained in U. So this expression over here, that's basically a test of whether these sets are open or not, and we're going to collect up all the sets that have that property. That constitutes our standard topology. Now, in fact, what I've given you so far is just a set of subsets. We actually don't know if this is a topology yet, because remember, we still need to check the axioms. So let's go ahead and do that. So what is the first axiom over here? The first axiom simply states that the whole entire set, which is the Rn we're considering, and the empty set must be in this standard topology. So Rn is pretty straightforward because, yeah, if you imagine, for example, R2 over here, for every single point, and for every radius, this open ball is always going to be contained in Rn. So I won't really write that up because it's very obvious. Now for the empty set is quite interesting, because if empty set was in the topology, then it must be that for all points x in your empty set, there exists some radius such that Brx is contained in the empty set. But you'll notice something funny going on over here, because the empty set has absolutely nothing in it. And over here we're saying for all points in the empty set, this condition must be true. Now, if there's nothing in the empty set, then there's no need to check this. So this whole entire proposition is actually going to be true. And if that's not convincing enough yet, you can go ahead and look up some propositional logic, and hopefully that will convince you. But yeah, it's kind of like from something false, you can prove anything. So false implies true. This is kind of like what's happening over here, because this statement, x is in the empty set, that's false. So from something false, everything is true. So yeah, look up some propositional logic if that's not really convincing yet. But this empty set, it's going to be in the standard topology because, well, it satisfies our condition. Okay, so now let's check condition 2, which states that if we have two neighborhoods, or two sets U and V, or two subsets U and V that are in our the standard topology, it must be that their intersection is also in the standard topology. Okay, so there's kind of two cases to this. If U and V are disjoint, so if we have two neighborhoods over here that are disjoint, then that intersection is the empty set, but the empty set is already in the standard topology. So the other case is if there's a little bit of an intersection going on, if they overlap a little bit, there's going to be some points that are in there. Okay, so let's choose a point X that's in the intersection. So we're going to let X be in the intersection of U and V. Now, if X is in the intersection of U and V, well, obviously X is in U and X is in V. So this is clear. Now we're assuming that U and V, those are already in the standard topology, which means they're nice and open sets. Over here, they don't contain the boundary. So if X is in U, so let's say this is U over here. If X is in U, then we must find a small little ball around that that's still contained in U. Same goes for V. So let's say that's V. So yeah, open boundary and so on. So we can write this down a little bit more precisely as being what this implies, since U and V are in the standard topology, that there exists some radius, let's call it R1, such that BR1 of X is contained in U. And also that there exists some other radius, let's call it R2, such that BR2, X, is in V. So intuitively, if you draw up a little picture, here's U and V, here's X over here. If X is in U, then there exists some radius such that this ball is in U, and for V as well, there's some little radius there. So now what we're going to do is we're going to define a new radius R to be precisely the minimum of R1 and R2. So we're going to take the minimum of those two radii there. And if you do so, then this implies that BR of X is in U and BRX is also in V because you're taking the minimum. So that's clear from the picture. If you take this a smaller radius, then that open ball will be in both of the sets. So if this is the case over here, if they're contained in U and in V, then this implies that BRX is actually contained in U intersect V. So what we conclude from this is that, yes, since there exists this radius, U intersect V is also in the standard topology. So the intersection of two open sets is also an open set. And let's check the third axiom, which is if you have a collection of open sets, U alpha, in your standard topology, we have to check that the union of all these alphas, so A, that's just any arbitrary index set of U alpha, is also in the standard topology. Now this is pretty obvious because if you have a bunch of these open sets and you union them all together, well, if you take some point, because it's always going to be in at least one of these open sets, you're always going to be able to find a small little radius. So yeah, the whole entire union will be open as well. So yeah, what we're going to do, we're just going to simply take some arbitrary U in this collection U alpha. And of course, U is definitely in the standard topology. But if U is in the standard topology, then for all points X in U, there's going to exist some radius R such that BRX lies in U. But since U is just a particular one of these subsets that we're pulling out, this also lies in the union. So this is also included in the union of all these U alphas. So that means no matter which neighborhood you take, for every single point, there's going to exist some ball where the whole thing lies in this big union. So the third axiom is also satisfied. So all these axioms over here, they check out. So what we can conclude from this is that the set Rn, if we equip it with this special standard topology, this is a topological space. And this standard topology is basically the topology I'm going to be using every time I speak of Rn. Of course, as I said before, there's many other topologies on Rn you could define, but the standard topology, that kind of models the Rn that we know. It models the way we think about this nice two-dimensional space and three-dimensional space and the real line and so on. It models how we think of it in the real world. And yeah, it's also consistent of how we understand continuity and convergence and a bunch of other properties on the real numbers. But yeah, hopefully you guys enjoyed it and learned something new. So up until the next one, have a wonderful day, and I will see everybody next time. Bye bye.